Hello. In this episode, we will together discuss the first kind of a game. So it's called strategic game or the simultaneous move game. Okay. Okay. So because this is the most simple game form that we can have, so let's start with this. So let's say that capital N is a finite set of players. Okay. And AI is a non-empty set of actions of player I. Okay. Non-empty set of actions of player I. Okay. Belonging to set N. Okay. And we also have a preference relation. Okay. So we use this notation, weakly preferred, for agent I, for player I. Okay. So this is a preference relation on what? So it's a relation on the Cartesian product of all the AIs. Okay. So we use this X. So this is a notation for the product of the sets. J from N, and we multiply all those AJs. Okay. Of player I from N. Okay. So we can also call this as the outcome of the game or as the action profile. Okay, because it's a combination of all the actions, right? Action spaces. Okay, so now we have the preference relation, and then we can define our utility, right? Utility function. So UI is a map from the action profile to a real number, okay? Which represents the preference relation that we have, right? Okay. So a strategic game could be denoted by a tuple, right? So let's see. So a strategic game, right, could be denoted by a tuple. So which includes the elements that we mentioned previously, right? So n players and the action spaces and the utilities, right, for each player. Okay, so that's essentially the what does the strategic game mean, right, or the simultaneous move game. And sometimes, even though the players are not move, they're not moving simultaneously, but we can regard them as a simultaneous move game because the players they do not cannot distinguish who is moving first or a second. So they are essentially the same thing. Okay. So let's have some examples. Okay. So the first one will be the very famous example in game theory. It's called Prisoner's Dilemma. Okay. Prisoner's Dilemma. Okay. So we use a form or a table to denote the actions for the two players and their payoffs, right? Their utilities. Okay, so we use the role player to denote the player one on the rows and use the columns to denote the player two. Okay, so player one or player two could either choose defend or confess, right? D or C. Okay, so each of the players have the same actions, either defending or confessing. Okay, so given those actions, then they can have some payoffs, and we use this table to do the payoffs. So let's say if both players defend, then each of them gets 3 as the utility. Okay, 3 and 3. If player 1 chooses D and player 2 chooses C, okay, so in this case, so the person who is defending actually doesn't work, right? So this defending is not working actually. So this leads to 0 for this person and gives a higher utility for the other one who is confessing. Okay, and similarly we have 4-0 here. And if both players they're confessing at the same time, then we have 1 and 1. Okay, so that's the very first beginning example of the simultaneous move game. Okay, and if later we'll introduce some solution concept called Nash equilibrium to help to predict and explain how the players behave in a steady state or in an equilibrium, right? So that's called the Nash equilibrium, and those are some solution concepts that we're going to discuss. So for now, intuitively, we can see that if player 2 is choosing D, let's suppose player 2 is choosing D, then in this case it's obvious that player 1 must choose C to get this 4, right? So because 4 is higher than this number. Okay, so if player 2 is choosing C, then player 1 is also choosing C to get this 1 instead of the 0, right? Okay, so similarly, if player 1 is playing D, then player 2 is choosing C to get this 4. And if player 1 is choosing C, then player 2 is still choosing C to get this 1. Okay, and you can see that in this corner, both two players, they have a sort of agreement, and we know that this is called a Nash equilibrium, right? Because in this case, no player has any incentive to deviate from this equilibrium. So in this case, each player has actually this is a dominant strategy, Nash equilibrium, right? Because no matter what the other player is doing, this player is always choosing C in this case. Either player 1 or player 2 in our game is choosing C. So we have this dominant strategy Nash equilibrium, which gives the payoff for each player as 1. Right? Okay, so that's the and later we'll formally define those solution concepts, and no worries about those things. So that's the first beginning example, and we can have some other examples to show the possible instances for the games. So the other one is called hawk and dove. Okay. So let's say those are two players that they could be either aggressive, so it's so-called hawk, right? Or it's not aggressive, so it's so-called dove, right? So there are two kinds of moves. So player 1 could be dove or hawk. The same for player 2, could play either dove or hawk. Okay, so let's suppose their payoffs are such that they can get 3 and 3 if both are playing D. And they're getting 1 and 4 if one is playing D and 2 is playing H. And symmetrically 4 and 1 and 0, 0 here. Okay. Alright. So if player 2 is playing D, then player 1 is playing H to get 4. Right? But the difference between this example and the previous one is that if player 2 is playing H here, then player 1 is choosing D, right? Okay, and similarly, if player 1 is choosing D, then player 2 is having H. And if player 1 is choosing H, then player 2 is choosing D. So we can see that there are two Nash equilibrium here, and we'll later discuss the concept for the Nash equilibrium. But here, intuitively, you can see that those are the two possible outcomes for this game. Right? Okay, so that's Hawk and Dove. And another very famous example in the simultaneous move game is the matching pennies. Okay, let's say those two players, they're choosing the head or the tail of a coin. Okay, so if those two, if the two coins they match, then the player 1 gets utility of 1, and player 2 gets -1. Otherwise, if those two coins they do not match, then player 1 gets -1 payoff, then player 2 gets 1. Okay, so that's essentially this matching pennies game. Okay, so let's say the first coin could be head or tail, and the second one could be head or tail. Okay, so namely we have the payoffs such that this is 1 and -1. Okay, if they match, 1 and -1. So if they do not match, then we have -1 and 1 here, and -1, 1 here. Okay, and we can see that if player 2 is choosing H, okay, and player 1 is choosing H to get this one. If player 2 is choosing T, then player 1 is choosing T. Okay, so if player 1 is choosing H, then player 2 is choosing T, and player 1 is choosing T, and then player 2 is choosing H. So we can see that there is no pure strategy in Nash equilibrium, and we'll discuss what does the pure strategy in Nash equilibrium mean. Okay, so intuitively it means that there is no stable or there is no actual prediction for this outcome of the game, right? Okay, so that's matching pennies. And the last example would be the battle of sex. Okay. All right. Let's say a couple, they're going for a date on the weekend, and they're choosing to go to either to go to a concert for Bach or Stravinsky. Okay, so they can choose either B or S, and player 2 could choose B or S. Okay, so if they match, then they can get a positive utility. If they do not match, then they get zeros. Okay, let's say B and B gives 1 and 2, SS gives 2 and 1. Otherwise, they get 0 and 0. Okay, and similarly, as what we did previously, we can see that those two are the Nash equilibrium for this game. Okay. All right. So those are some interesting examples that we can use to illustrate the basic idea of the simultaneous move game, or the so-called the strategic game in the textbook of Osborne and Rubinstein. Okay. So that's the very first, the most simple form game, simultaneous move game that we discussed today. Okay. All right.